So, have you ever stopped to wonder how a tiny Silicon Valley startup, literally founded by three guys eating breakfast at a Denny's, somehow became the absolute most critical infrastructure provider of our entire modern era? I mean, it's wild to think about. It's a story of near bankruptcy, these massive, completely company-risking gambles, and a vision of computing that literally changed the world we live in.
Because today, we are talking about a company that recently shattered records to reach a truly staggering $3.4 trillion market valuation. $3.4 trillion. They now power over 90% of all AI model training globally. The sheer scale of this story is just immense.
So, welcome to this documentary explainer. We're going to be unpacking this incredible history, digging into the underlying hardware, and examining the massive strategic moat of NVIDIA, really to see exactly how they built the silicon hegemony of the 21st century.
Okay, let's dive right into this. We'll start with Section 1, a diner, $40,000, and GPUs. Then Section 2, the costly CUDA bet. Section 3, breaking the hardware bottleneck. Moving on to Section 4, the generative computing paradigm. And we'll wrap up with Section 5, entering the physical AI era.
All right, Section 1, a diner, 40K, and GPUs, the genesis and the gamble. Our story actually takes us back to April 1993, to a booth at a Denny's in East San Jose, California. Three engineers looked at the computing landscape and made a massive bet that parallel computing would be the future. So founders Jensen Huang, Chris Malachowski, and Curtis Preem started NVIDIA with just $40,000 in the bank. And, it was far from an overnight success. Actually, their very first product in 1995, the NV1, was a total commercial failure. It entirely drained the resources and quite literally nearly drove them to bankruptcy. But they fought, they survived, and they pivoted. By 1999, they launched the GeForce 256. They marketed it as the world's first GPU, or graphics processing unit, which successfully offloaded heavy 3D graphics rendering from the computer's main CPU.
Moving into Section 2, the costly CUDA bet, laying the AI foundation. Now, the invention of the GPU was obviously huge for PC gaming, but the real turning point for the company, and honestly for the rest of the world, came in 2006. This was arguably the most dangerous and important decision in their entire history.
Jensen Huang had this radical philosophy. He said, install base defines an architecture. Everything else is secondary. Following this, he insisted on putting a brand new software platform called CUDA on every single consumer gaming card they made. He was basically heavily subsidizing the cost of a parallel computing platform just to get it into the hands of millions of people.
So, what does this all mean? Why was CUDA so absolutely crucial? Well, because it completely changed what a GPU could actually do. Instead of just doing graphics rendering, processing polygons for 3D video games, CUDA unlocked general-purpose parallel computing. This meant developers could suddenly use standard C code to run scientific simulations, molecular dynamics, and super complex math simultaneously across thousands of tiny cores. Basically, GPUs stopped just rendering game graphics and started processing staggering amounts of data.
Now, what's really interesting here is that adding this CUDA functionality cost an absolute fortune to develop. And PC gamers, they didn't want to pay extra for scientific computing features they were literally never going to use. This so-called CUDA tax was absolutely hated by Wall Street, and it ended up tanking NVIDIA's market cap from around $8 billion all the way down to $1.5 billion. It was a brutal financial reality. But secretly, this massive company-risking gamble built the exact foundation needed for the 2012 AlexNet breakthrough. That's when researchers realized these subsidized gaming cards were the absolute perfect engines for deep learning.
Let's move to and see how this builds in Section 3, breaking the hardware bottleneck, the rise of AI infrastructure. Because once the AI boom actually started, a new problem quickly emerged. Standard data center servers just couldn't move data fast enough to feed these incredibly hungry GPUs. The AI era demanded entirely new computing architectures.
You see, the traditional PCI cables connecting server components were essentially like a one-lane dirt road for data. So NVIDIA invented NVLink. This is a revolutionary high-speed GPU interconnect mesh that completely shatters that old traffic jam. It provides up to 5 times the bandwidth of standard PCI links. And this is the exact technology that allowed massive supercomputers, like the famous DGX-1 that Jensen Huang personally donated to OpenAI back in 2016, to act not just as a collection of separate chips, but as one giant, unified brain.
So the crucial point is the sheer exponential physical scaling required to feed modern AI. These are the chips powering the AI tools you are probably using every single day. Look at this jump. In just a few years, we go from the Hopper architecture packing 80 billion transistors all the way to the upcoming Rubin architecture boasting an astronomical 336 billion transistors and 3,600 gigabytes per second of bandwidth. It's insane. They are practically printing supercomputers to keep up with the world's demands.
That brings us to Section 4, the generative computing paradigm, a new industrial revolution. But hardware is only half the story, right? To really grasp NVIDIA's master plan, we have to shift from the silicon itself to their overarching philosophy for the future of the internet.
And this brilliantly illustrates the shift. For 60 years, we lived in a world of retrieval-based computing. You click a link, and a server retrieves a pre-recorded video, an article, or stored data, right? The output existed long before you even arrived. But NVIDIA's core thesis is that we are actively moving to generative computing. Based on your live context and intent, the system generates novel text, images, and audio as tokens in real time. We are moving away from a world of static data storage to a world of live intelligence generation.
Because of this paradigm shift, data centers are no longer just giant file cabinets, they are AI factories. They are literally the new power plants of a new industrial revolution, operating as massive token generators. And as you can imagine, this requires a massive reindustrialization effort across the globe. It demands incredible amounts of energy and a fundamental modernization of our electrical grids, all just to power the generation of these AI tokens.
Which perfectly sets up Section 5, entering the physical AI era, Project Groot. This is the final frontier of NVIDIA's master plan. What actually happens when we take AI out of the server rack entirely and put it into the physical world?
To achieve this, NVIDIA built the Jetson Thor. Now, this isn't just a server chip. This is a jaw-dropping engineering feat. It's a computer designed specifically to go inside a humanoid robot. It packs a Blackwell architecture GPU that delivers over 2,000 teraflops of performance, paired with a 14-core ARM CPU. And this platform is built entirely to run Project Groot. That's NVIDIA's foundation model designed specifically to bring deep reasoning, natural language understanding, and fluid dynamic movement to physical robots.
From a $40,000 diner startup to a $3.4 trillion silicon hegemony, NVIDIA has effectively built the engine of the digital AI revolution. But as we look at platforms like Jetson Thor, I really want to leave you with this final thought to ponder. We've seen how AI has transformed text, images, and code, but what happens to our world when AI tokens leave the digital realm entirely and autonomous, embodied intelligence starts moving alongside us in the physical one?